Okay, ladies and gentlemen, welcome back to another chapter. So this week we are officially moving on to chapter 3, and chapter 3 has a very ominous title called Vectors. And to give you some context as to what I'm kind of alluding to, most vectors in physics, most variables in physics are vectors. There are only a few variables which are not vectors. They are in the minority. Vector variables are in the majority. So you're going to be dealing with vectors and whatever they represent, starting in this chapter, pretty much for the rest of your life until you die. You might like them, you might not like them. That doesn't matter. Vectors don't care what you think, they are what they are. It's important for us to be able to understand what they are and how to use them to solve complicated problems, especially in future chapters. So first things first is for vectors. We are initially going to be focusing on what we're going to call R2. And I guarantee that you've seen this symbol in a previous math class, or maybe if you were lucky in several previous math classes. R2 is basically a two-dimensional metric, sometimes referred to as a coordinate system. If you want to really be lowbrow about it, it can also be called a graph. Coordinate system is better. Two-dimensional metric is very fancy, very highbrow. But if you wanted to kind of be very lowbrow about it, a graph would be okay. Just kind of be aware that people will laugh at you, especially in the higher circles, if you say that. But we're going to be focusing on two-dimensional variables, two-dimensional values. And what we're going to say about this is that for our vector, it's going to be any variable which can be expressed as an arrow within a frame of reference. And that phrase, frame of reference, is going to pop up very importantly within chapter 4 and beyond. But for right now, we're going to say that frame of reference is really just a fancy phrase for a coordinate system, specifically one that has an origin associated with it. But nonetheless, if we focus on a very simple variable, the idea of location, let's just say that we have the point P, and this point P is located in this first quadrant of a graph, which technically should have 4 because it is two-dimensional. I just have omitted the second, third, and fourth quadrants of this coordinate system, of this graph, if you will. And to keep things simple, we're just going to call the horizontal axis X, and we're going to say that the vertical axis is Y. And each one of these little lines represents one value. Could be time, could be distance, could be length, could be anything. We really don't care about the units that give the variable context. Right now, we're just focusing on the basic idea of what a vector is. We'll give it context later on in chapter 4 when we're ready. But what we're going to say is that the position of point P relative to the origin, and that's going to be a really crucial thing in chapter 4, but the position of point P relative to the origin can be expressed as a vector, as an arrow within this frame of reference as follows. And what you're going to notice about this arrow is that the head of the arrow, which we're going to call the tip of this arrow, is specifically oriented towards point P, and the other end, the tail, which we're going to go ahead and just call the tail in this case, starts off at the origin, because that is our point of reference. That is our kind of basis of description. It's kind of like, for example, when somebody asks you for directions in person, you're going to give them directions to wherever they're going from where you are, because you are the point of reference in that context. The arrow itself, tip and tail, these are two words that are going to be used throughout this chapter and throughout pretty much the rest of the semester whenever we deal with vector quantities. And you'll notice that I've called this vector R, and I've given it a little arrow symbol above it. Whenever you see an arrow above a letter, maybe 2 letters, worst case scenario, but usually most variables have 1 letter. Whenever you see the arrow above the letter, that designates that the quantity in question, the variable in question, is in fact a vector quantity because it has an arrow which can describe its behavior. But every arrow has a tail at the bottom connected to the origin usually, and then every arrow has a tip pointed away from the origin towards a point of interest or towards some numerical value. So this is going to be our kind of starting point for drawing arrows. But what we're going to do is we're going to go ahead and describe that vector, the position of point P, quantitatively. And we're going to go ahead and describe it using the following symbols, using the following notation. And what you're going to see here is that the point P is described as 3, 4. And now why is that? Because it's kind of 3 here and kind of 4 there. But you'll notice that I've set that equal to a very interesting subtraction involving x coordinates, 3 and 0, and y coordinates, 4 and 0. And it seems kind of odd why I'm doing that, but again, subtract 0 from any number, the number itself does not change. So I can subtract from 0 anything, and I get the same exact result. That's a freebie, in effect. And there's a reason why I'm doing this. There's a method to my madness. And the reason for this, the method to my madness, is how I manipulate the subtraction that I've put on the right-hand side. So what I'm going to go ahead and do is, because 0 is neither positive nor negative, minus 0 plus 0 is the same thing. So I'm just going to reorient the second part of my coordinate description. So 4 minus 0 is the same thing as 0 plus 4. All right. Seems like I didn't do much, but again, there's a method to the madness. It happens in the next step. What you'll notice that I've done is I have separated the first x coordinate and the first y coordinate, and I've separated the second y coordinate and the second x coordinate as separate identities, separate quantities that are now being distinctly added together. So these 2 points together is still 3 plus 0, 3 minus 0 being the same thing. 0, 4, okay, they're still added together, nothing really changes. But I've put the expression, I've put the point 3, 4 in a very interesting format. What do I mean by that? Well, I can factor out 3 from the first term and 4 from the second one. When I factor out the 3 and the 4, all that I have left is a very simple expression of 1, 0 and 0, 1. And again, that might not seem like much, but we're going to be going somewhere very special with those two symbols, those two x and y coordinates that I've kind of left behind from my factoring. Specifically, the way that we can think about this is that if I redraw that same vector, I didn't put the r in here because it was getting crowded, but if I redraw that vector one more time, the key thing is that to get to point P, I move to the right 3 times. So to the right, to the right, to the right. So here's 1, 0, here's another 1, 0, and here's another 1, 0. And it gets me to this horizontal location. And I can do the same thing for the y direction. Here's 0, 1, here's another 0, 1, another 0, 1, and another 0, 1. There's 4 of them that I need to stack end to end to end to end to get to the proper height of point P. So I'm describing the location of point P by moving in separate directions, multiple times horizontally, multiple times vertically, but they both together take me to the point P. But when it comes to physics and mathematics too, we really don't express vectors in terms of x and y coordinates. It's usually not done. So what we're going to be doing instead is we're going to introduce the idea, we're going to introduce the concept of a unit vector. And it turns out that a unit vector, quite simply defined, is a vector of unit length. All right, well, when we say unit length, what do we mean? Well, quite simply, we mean that the vector has a length, as measured with a ruler or some other measuring device, of 1. Now that could be 1 inch, 1 yard, 1 kilometer. We really don't care at this point, but it has a length of 1. The word unit in mathematics is a very special word. It just means 1. So this idea of a unit vector, a length of 1, what the heck do we mean length of 1? What do we mean unit length? Well, to understand that, let's go ahead and kind of break down our vector in terms of triangles, specifically right triangles. And if you look at this picture that I've redrawn, the tip of the vector has been removed because right now it's not necessary to this part of the understanding of a vector. But what I've done is I've left in the 2 base values, 1, 0 and 0, 1, because again, I needed to move to the right 3 times to get to the proper horizontal location, and I had to move up 4 times to get to the proper vertical location of point P. So by adding in this dotted line here and dotted line here, kind of like I did as well, if I imagine that this is part of a triangle, this is part of a triangle, and my vector itself is basically the hypotenuse of this imaginary triangle, then the key thing is that I know that this side of my triangle is 3 and this side is 4. So using good old-fashioned Pythagorean theorem and other ideas from geometry, I can figure out specific values, specific numbers that describe my vector in very helpful ways. So for example, the length of this vector, P, question mark as I'm calling it here, it's basically Pythagorean theorem of an adjacent side being 3 and an opposite side being 4. And basically it's a 3, 4, 5 triangle. So if I use Pythagorean theorem, it just means that the value of question mark, the length of my vector, the magnitude of my vector, as we're going to be calling it throughout chapter 4, is just going to be a value of 5. Okay, so how does this relate to unit vectors? Well, if I look at these little specific arrows here, there were 3 of them that were horizontal, I've just kept 1. There were 4 of them that were vertical, I've just kept 1. If I look at these little vectors themselves, this vector right here, it had 0 for an x coordinate and 1 for a y coordinate. So it has a length, it has a magnitude of 1, which is unit. So it means it's a unit vector. This guy right here, it had a coordinate of 1, 0. So if I take the Pythagorean theorem of that, I get 1 squared plus 0 squared, which is still effectively 1. It's another unit vector. So both of those little black vectors that I've drawn, they represent unit vectors, and that's why I've kept them in this secondary picture of my point P description. Just for simplicity, we're going to say that this is a unit vector that is horizontal, and this is a unit vector that is vertical, aka x is horizontal, y is vertical. Not really terribly surprising, but it's going to be extremely relevant in chapter 4 and beyond. But it turns out that by using Pythagorean theorem, we can figure out the length of this vector, the magnitude of the vector, which is basically just the hypotenuse of our imaginary right triangle. But it turns out using other aspects of geometry and trigonometry as well, we can reference the interior angle, which is made between the x-axis, which is a common reference point in trigonometry and geometry, and the vector itself, which is labeled by question mark in this case. So here's kind of what I'm referring to. So I have my 3 horizontal, my 4 vertical, and now my 5 hypotenuse. And right now I just kind of want to figure out what is the angle of inclination? What is the angle that my vector makes to the horizontal, to the x-axis, a typical trigonometric reference point? If I use a little bit of geometry / trig, SOHCAHTOA stuff, sine of theta is 4 divided by 5, opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse, 3 divided by 5. And tangent is opposite divided by adjacent, so 4/3 in this case. Nothing terribly surprising because this is a 3, 4, 5 triangle, But the nice thing is that I can figure out the value of theta. I can figure out the directionality of my vector, in this case to point P, in a now numerical sense, in the context of like a compass, for example, which is very helpful for like navigation and things like that. But there is one small disclaimer that I need to mention at this point. What is that disclaimer? Well, simply put, whenever you use the symbol theta in a test, on a quiz, in a homework problem, theta is always an acute angle. It was in geometry, it even is in trigonometry. And in this class, Physics 4a, theta must be an acute angle. It could be 0, it could be 90, it could be anywhere in between, but it can't be 91. We're going to be using a different symbol for obtuse angles. We'll talk about what that symbol is a little bit later on. But this is important because if the angle theta is an acute angle, that means that the output of the sine, the cosine, and the tangent, when you take the inverse, they're all positive because you're in quadrant 1 of a 4-quadrant system from trigonometry. That's going to be helpful a little bit later on. Okay, so what we can do is using our SOHCAHTOA relationship on the top, SOHCAHTOA relationships on the top right of this page. What we can do is we can rewrite our vector equation a little bit differently. I can get rid of the 3 and put in 5 cosine of theta, and I can get rid of the 4 and put in 5 sine of theta, like you see that I've done here with my 2 brackets. Now, that doesn't seem like a very helpful thing, but by doing so, what's in common to both terms now? The value of 5, the magnitude of the vector, the hypotenuse of our triangle. There's now a commonality between the 2 terms. It's always a nice thing in physics. But it turns out that in physics, we can do even better. So for example, in physics, we don't like to leave vectors in XY coordinate form, in kind of point form, basically. That's good for graphs, but it isn't really good for calculus and arithmetic and other calculations. So what we're going to do is introduce special symbols for these unit vectors. The 1, 0, the horizontal one, and the 0, 1, the vertical one. And we're going to give them the following symbols: I and J, I for horizontal, J for vertical. But because they are unit vectors, not just any regular old vector, but because they are unit vectors specifically, a subcategory of the vector family, we give them not an arrow above the letter I, not an arrow above the letter J, but a little hat, or a caret is it technically called in English, above the I and above the J. The dot is absorbed, it just is what it is. But this is a much simpler way to write the vector. In a similar sense, since we're talking about the position vector or the position of point P, instead of kind of using the kind of algebra 1 notation of P colon 3, 4 parentheses, we're just going to use R with the vector, position vector, R arrow in this case. And what that allows us to do is it allows us to rewrite the vector, the position vector, in a much more simple, compact form. The first term is completely separate because it's really a coordinate in disguise, but this is a much more calculus-friendly symbol, as you'll find out in Math 4a and above. Same thing with J hat. This is a special symbol, so I can't just add these 2 together. They're not really numbers, they're distinct pieces of information, kind of like they were before in the previous step. But this is a much more concise, much more boiled down version of describing the position of a point in a graph, a point in a coordinate system, a point in a frame of reference, than the previous ways that I've written them, that were much more bloated in comparison. It turns out that specifically, 5 is the magnitude of this position vector. And if I wanted to kind of describe any position vector, not necessarily to our point P, but to any possible location in quadrant 1, then I would use this very special symbol for the value of 5. And what I want you to kind of notice is that it's the R vector symbol, but it has 2 lines that are parallel to each other on left and right-hand sides. For those who plan on going into graduate school or who plan on taking math at the upper division, these are symbols that are going to be used very often in those math classes. Now, this is something that's different from our textbook, because what our textbook does is they're kind of stuck in the old way of thinking, a way that's falling out of favor, becoming less common. The old way of thinking, which I'm never going to do, is using the absolute value symbol with the R vector symbol inside. Now, that's common in many physics textbooks. But again, if you go to the higher levels of physics and the higher levels of math especially, they never do that. The reason why is that in math, the absolute value function is defined only for scalar values. It is not defined for vector functions. It gives garbage. It is nonsense. You are destroying a definition, which you can never do in mathematics. So that old way of thinking is slowly dying, emphasis on the word slowly. So if you want to put absolute value symbols around the R vector symbol, it's not wrong, but just be prepared to get made fun of when you go to the higher levels of classes. I hope you have some thick skin, put it that way. I strongly recommend using these symbols right here. However, there is another option. Specifically for physics. In math, they do not do this. But in physics, we have one other choice. If you really aren't comfortable using the double parallel line symbols surrounding the vector in question to designate hypotenuse, magnitude of vector, the other option that you have is to remove the actual arrow itself and write just the letter. The letter without the arrow designates the magnitude of the vector. And this is something that when we get to chapter 4, I'm going to call a throwback, or I'm going to have a throwback to chapter 2 when we talked about the idea of speed versus velocity. But nonetheless, this version on the right-hand side, this is one that's used very often in physics textbooks. In math, they never use it. In engineering, sometimes they do, sometimes they don't. But for physics, this is okay to use too. I'll kind of use this one a lot, but I will use this one often as well because it's easy, it's lazy. But for us, either form is fine. But it turns out that because we have written this vector in a very specific way, R cosine theta for the horizontal component of the description, and R sine theta for the vertical component of the position's location, I hat versus j hat. This is called the polar coordinate form of a position vector. Why is it called polar coordinate form? Well, R is kind of like a radius and theta is like an angle, because again, the way that you can think about this is using your imagination. Start the vector at 0, rotate it up to the point in question, and then stop. You've rotated through an angle theta along a circular arc. So therefore, polar form, aka circular form, makes a lot of sense. It's basically just trigonometry in disguise. But especially for those of you taking Math 4A, you're going to hear that phrase quite often, polar form of this, polar form of that. It's very, very common to use when dealing with circular behaviors. Okay, well, it turns out that we can also describe the vector in a different form, not necessarily polar form, but something else which may or may not be easier depending upon the problem. So what I'm going to say is that R cosine theta can be represented by R subscript x, and R sine theta can be represented as R subscript y. This is the x component of this arrow, which is R cosine theta because it's the adjacent side of the right triangle. This is the y component of the position vector because it's basically the opposite side, the vertical side of this right triangle that I'm referencing with the theta symbol right here. But in most physics textbooks, they don't write R subscript x for horizontal position and R subscript y for vertical position. I wish they did, but they don't. Instead, they just use the letter x and the letter y for horizontal and vertical position. This is called the standard form, sometimes also called the Cartesian form of the position vector. Why is it Cartesian? Because it's given in terms of coordinates, x and y, just being numbers along the x and y axes of our frame of reference. Our sine theta, our cosine theta are more terms of circular behaviors, rotating through an angle at a distance away from the point of reference. Whereas x and y are just move to the right, move to the left, move up, move down to get to the point in question. So in chapter 3, we can get away with the standard form, the Cartesian form of vectors in most cases, ... but not in all cases. In chapter 4, we're going to find that the Cartesian form of position vectors, or just the Cartesian form of vectors, isn't as helpful as it might seem. The polar form actually will give us more insight into an object's behavior. If you plan on taking Physics 4b, electricity and magnetism, you pretty much have to express everything that's two-dimensional in polar coordinate form. Cartesian form will be a horrible mistake to make, and I'll wait for you to see that when you take that class with Dr. Sim, Dr. Spinella, or if the kind of luck is right, then maybe myself, but I'm pessimistic about that. I haven't been lucky in the drawing these past several years. But nonetheless, for a position vector that was in any quadrant, the second quadrant, the third, the fourth, not necessarily having to be in the first quadrant like ours just happened to be, we want to rewrite the polar form of our position vector more generally. So we're going to say that x and y, the Cartesian representation of the horizontal and vertical components of the vector, we're going to keep them in polar form, r cosine, r sine, but we're going to change the symbol from theta, which is an acute angle only, to alpha. And alpha can be acute or obtuse. To be specific, alpha is really just any angle between 0 and 360. Technically, alpha could even be a negative angle, but usually it's positive. In very, 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 very few cases have I seen it negative as the alpha symbol. The common kind of consensus among scientists and mathematicians, alpha is positive, let's just leave it positive. But the nice thing about alpha being between 0 and 360 degrees is it allows the x coordinate of the position to be positive or negative, and it allows the vertical position to be positive or negative. So if there was a positive x coordinate but a negative y coordinate, we're definitely in quadrant 4. Theta makes no sense. We need to be alpha because in quadrant 4, the angle is between 270 and 360 degrees. You could write it down as a negative angle, but again, that's very, very bizarre. In fact, I would strongly recommend against doing negative angles, except unfortunately some of our homework problems, not so much. And I'll talk about that a little bit later on in our disclaimer. So what do I mean by that? Well, alpha is measured, that's a typo, I am very sorry. Alpha is measured counterclockwise. Counterclockwise. Please make that change in your notes. Wow, that's a really bad one. I totally missed that. Alpha is measured counterclockwise, the way that angles are typically measured in trigonometry. You start off at the x-axis and you rotate counterclockwise until you come back to the x-axis and then start the whole thing all over again. In some of the homework problems, I'd say at least half of them, which kind of makes me barf, they actually want you to measure, and again, I got this backwards. I guess I'm having a really dyslexic day. They want you to measure the angles clockwise. So again, for this part of the lecture, change counterclockwise to clockwise for the homework problem disclaimer right here. My apologies, really bad on my part. The reason why is that even though the angles are negative, they're usually acute angles like negative 20 degrees, negative 30 degrees, negative 50 degrees. And in some engineering disciplines, mechanical engineering comes to mind, they like to deal with acute angles. They don't like to deal with obtuse angles, which as a physicist and a mathematician, I just kind of laugh at because a compass is basically 0 to 360 degrees. You can easily program that into a computer, and plus you don't have to worry about taking negative cosines and negative sines, which just don't work, turns out. But whatever, I digress. Just be aware that for some homework problems, they're going to say, find the angle of the vector measured clockwise. Barf, gross, diarrhea, whatever, just deal with it and move on. It's only about half of the problems. But for the rest of your life, it's counterclockwise. It's the trigonometry normal direction, the kind of default direction, the friendly direction. Okay, well, everything is hunky-dory, but there is one small issue, and that is in chapter 3 and also in chapter 4, we don't have to stay in the two-dimensional metric. We don't have to stay in R2. If we want to bump up to R3, aka left, right, up, down, and forwards, backwards, we have to introduce another unit vector, which we're going to call k hat, or k with a caret above it. It's going to represent the z-axis, or the z direction, in effect. And because it's now R3, then the unit vector symbols have to be written a little bit more complicated. So for example, it's not just 1, 0 for I hat, it's 1, 0, 0, because we have 3 axes that we are spanning, that we are dealing with. Same thing for j hat, 0, 1, 0, because we're now in the 3rd dimension. K hat is nice and easy. It's just 0, 0, 1 in the vertical, in the kind of azimuthal, or as we're just going to call it, the z direction. Now, with R3, polar form changes to spherical form. And if you take Math 4A, or if you've taken Math 4A, you know all about spherical coordinates, spherical forms of vectors. They are unpleasant to deal with because there are 2 angles. If you want to understand why, come to office hours and I'll draw you a couple of cool pictures from Math 4A. But typically in Physics 4A, we try not to deal with spherical form. We try to keep things in Cartesian form for 3-dimensional vectors, because having to deal with 2 angles in spherical form can be tricky. It's very realistic because many objects in the universe, stars, planets, comets, asteroids, are spherical in nature. So the spherical form of vectors makes total sense in the great spectrum of things. But if we're dealing with R3, we're typically just going to use X, Y, and Z for position vectors, for example. Just the numbers themselves, not necessarily putting them into a spherical form that involves a radius and 2 angles that you would have to rotate through to get to that very specific 3-dimensional location in a 3-dimensional coordinate system. Physics 4B, you'll start to touch on that stuff, so just be prepared, like was in The Lion King. But the unit vectors, if I want to find the magnitude of I hat, it's still Pythagorean theorem, but again, because we're in R3, polar form upgrades to spherical form. Circles upgrade to spheres, because spheres are 3-dimensional, circles are slices of spheres, they're 2-dimensional. For Pythagorean theorem, that's for a triangle. If we want to talk about 3-dimensional quantities, we go from a triangle to a pyramid. So all 3 numbers are squared. They're then added together, and we still get a value of 1. So I hat is still a unit vector. J hat is still a unit vector because its magnitude, its length is 1. And it turns out that k hat, our brand new unit vector for a 3rd dimension, is just 0 squared plus 0 squared plus 1 squared, added together, take the radical, still a value of 1. So we're still a unit vector, in effect. All right, well, everything that we've learned so far, whether it's for 2-dimensional, R2, or 3-dimensional, R3, it allows us to write down vectors in standard form, in polar form, or God help you, in spherical form, but we're going to keep it in standard form, just having X, Y, and Z. But usually, especially in chapter 4 and beyond, we don't just have a single vector that we are analyzing in great detail. Usually we have 2 vectors, and each vector is describing some property, some behavior of an object. But our goal will be to combine the 2 vectors together in some type of way, using some type of arithmetic. Unfortunately, the way that we combine vectors is not, and let me emphasize that one more time, not the same way that we combine scalars. AKA, if you want to add vectors together, the rules are 100% different than just adding two numbers together. Completely night and day difference. So for example, if you wanted to add two numbers together, you could do so. Scalar addition, 2 plus 3. If you wanted to subtract two numbers, 2 minus 3, sure, go ahead. When it comes to vectors, vectors can be added together, and that's it. Vectors can't really be subtracted. So that's the first kind of weird difference between them. All right, fine, whatever. When it deals with multiplication and division, if you want to multiply 3 times 4, sure, go for it. If you want to divide 3 by 4, great, go for it. When it comes to vectors, vectors can only be multiplied. It is 100% impossible to divide vectors. And I know because in my class in physics, I didn't pay attention that day. I had a question about vectors. I tried to divide them in front of my teacher, and the look on his face was just priceless, because it was just as if someone had tried to basically create a mountain out of their own feces. It's just like, what the hell are you doing? And he even kind of told me, you need to go outside and rethink what you've done and come back when you can see what you, that told me, because basically made me recognize, I have no idea what I'm talking about. I better kind of wisen up. And I did, thankfully. But it is completely impossible to divide vectors in the way that you could easily divide two numbers. So let's go ahead and kind of tackle our vector arithmetic, as limited as it seems, one idea at a time. So let's go ahead and deal with vector addition. And it turns out that vector addition, it can be understood, it can be interpreted in two different ways, really kind of using two different branches of mathematics. Vector addition can be understood algebraically, kind of like alphabet soup, just a bunch of symbols moving around. Or it can be understood geometrically, aka draw a bunch of pictures, see how they're related to each other, and then get the final information from that picture. It turns out that geometrically, vector arithmetic is actually a lot easier. Algebraically, vector arithmetic, including vector addition, is just lots of symbols moving around. It's just kind of alphabet soup. It's just kind of like throwing up alphabet soup. It's just kind of all over the place. It's gross, but I guess it's better than nothing. But because most people are more comfortable with algebra compared to geometry, I'm going to go ahead and deal with vector addition in an algebraic sense. So let's just say that we have two vectors, and I'm just giving them random letters, lowercase a and lowercase b. There are arrows above both of them, so these are distinctly vectors, not just numbers. This isn't 5 and 6. This has an I hat, j hat, maybe even a k hat component. This has its own unique I hat, j hat, and maybe even k hat component. And my goal is, how the hell do I add them together to get a final total result? So for simplicity, let's just go ahead and say that the vector A has only two components. It's an R2. It has an X component and a Y component. And we're not dealing with position, so I'm not going to just use X and Y. I'm going to use AX for the X component of the vector, and AY for the vertical component of this vector. Ditto for this guy. B subscript X for the horizontal component of this vector, B subscript Y for the vertical component of that vector. And if I go ahead and kind of just take these two very generic definitions of A and B, then even though the addition is bloated, this is my starting point for vector addition. Lots of symbols, alphabet soup, gross, but at least we kind of know what to do. We sort of have an idea of how to add things together. And the way that it's going to work now is kind of like when you add polynomials together, you add the like terms together. Specifically, what are the like terms that I'm adding? Anything that's an I hat, I want to bring them together. I want to associate them together because they're both talking about horizontal descriptions. Anything that's a j hat, I want to associate them together because they're both talking about vertical information. So I'm using the parentheses to associate horizontal and horizontal, another set of parentheses to associate vertical and vertical. But by using those parentheses, the associative property of algebra, which also works for vectors too, what I can do now is I can recognize that, you know what, a subscript x, it's a Cartesian coordinate. It's just a number, +5, -6, 0, whatever. Same thing with b subscript x. It's a Cartesian coordinate. It's just a number, 5, 10, -4, whatever it might be. But they both have the symbol of I hat in common. And just like in algebra, when two terms have something in common, what do instinctively? You factor it out. I factor the I hat out from both terms in the first set of parentheses. I factor out the j hat from both terms in the second set of parentheses. Admittedly, what I'm doing here is instead of putting the I hat in front, like you would typically do, and the j hat in front, like you would typically do, I'm putting it on the back because this is more of a standard form, a standard way of writing vector addition. But the key thing here is that as long as I add the x components of each vector together, that will become the x component of the total added together result. Ditto for the y direction, ditto for the vertical component of my vector addition. It's just ay plus by, vertical component of first vector, added to vertical component of second vector. And kind of like how our textbook does, if I just kind of let c be equal to a plus b, then this whole thing becomes c. So this is the x component of the c vector. This is the y component of the c vector. And therefore my c vector, it has a magnitude, it has a length that's given by Pythagorean theorem as x squared plus y squared under the radical, which in this case is rather complicated, but still can be now understood in terms of the two vectors a and b that went into that process. Okay, side note. If I were to add the vectors together oppositely, not 2 plus 3, but 3 plus 2. Ooh. If I were to add them together using the same logic, I would get this result at the end. B is first, so it's first. A is second, so it's second. But again, AX and BX, these are just Cartesian coordinates. They're just numbers. And whenever I have numbers, aka scalars, the order doesn't matter. -5 plus -2 is the same thing as -2 plus -5. The order of addition is invariant for scalars. And that's what these guys are. They're just basically numbers. They're basically scalars. So if I change the order of addition, it's still the same thing. But by changing the order of addition, I get this result from before. So what that basically means is that vector addition is order invariant, which is kind of a nice connection to scalar addition, which is also order invariant. Now, just kind of like the Offspring song, I have to keep the components separated. So I can't add together the I hat and the j hat. They're completely separate. They never merge together. So they remain distinct, but the order that I add the vectors together in will output the same result no matter how I do it. So that's one cool thing about vector algebra, is that it is similar to scalar algebra, scalar addition, in the sense that the order of addition doesn't matter. All right, well, that was algebraically, a bunch of symbols floating around. What about with pictures? What about geometrically? Well, it turns out that if you want to add vectors together graphically, there are two ways to do it. And we're actually going to be doing a lab about how to draw vectors together, adding them, and weirdly enough, kind of subtracting them by using both of these two methods that you see right here, something called the parallelogram method and something else called the tipped tail method as well. Both methods work, they just have different restrictions and they have different difficulties in using them, aka you might find one easier than the other. Just watch out because one of them has a very strong restriction when it can't be used. The other one is more broad in comparison. So the parallelogram method, it basically states that you need to construct a parallelogram, which is just a four-sided object like a cube, like a square or a rectangle or a rhombus, diamond shaped, something like that, with the two vectors that you're trying to add together. Might not make a lot of sense right now, but I will show you pictures momentarily. The tip to tail method, my personal favorite, is basically connect multiple vectors together, and that's it. It's a loaded statement. There's actually a lot going on in that definition, but it's actually quite easy, in my opinion. But we're going to look at both, because both of them might be able to be used to solve a problem. One definitely, the other maybe, maybe not. But let's just go ahead and say that we have two vectors. Vector A is in quadrant 1, and vector B is kind of straddling the butt crack of quadrants 3 and 4. So it's at an angle of 207 degrees, if you want to be picky about it. Vector A is around 45 degrees. I don't know, I didn't draw it to scale. I wasn't using a protractor, so I just eyeballed it. But those are the two vectors, and we want to add them together vectorially. We want to add them together graphically, geometrically, as we're going to call it. I don't have any numbers, so I really can't use the algebraic method. I'm kind of stuck at this point. But let's go ahead and look at the parallelogram method. Both of these vectors are connected together at the origin. So I can think of this as one side of the parallelogram, of which there are 4 sides total. This is a separate side of the parallelogram, so that's now 2 of the 4 sides together. And for the parallelogram method, all that I need to do is what I call close the box. It's basically taking the two vectors A and B and copying and pasting them to form a parallelogram. In this case, it kind of looks like a diamond shape in effect. But this is the vector A, copy and pasted to B to form the opposite parallel sides of a parallelogram. This is B, this is the clone of B to again form the other part of the two parallel sides of a parallelogram. Now, where is the resultant vector? Where is the addition of the two vectors? It is at the diagonal of the shape that I've created. So by me closing the box, this is the vertex of me closing the box. The vector addition goes from the origin to that diagonal, to that vertice right here. So that little arrow right here is the vector addition of A and B using this very specific method of making boxes and closing them by copying and pasting in effect. And then the diagonal of that box from the origin is going to be the vector addition of your two vectors. Now, what about the tip to tail method? This one is different because what you do is you take the second vector and you physically move it to the tip of the first vector, hence the tip to tail method. Here is the tail of the second vector. Here is the tip of the first, kind of like a human centipede kind of thing. I connect them tip to tail. And that's why I love this method, because it reminds me of the human centipede. I just connect one vector, tip to tail, and then another vector, tip to tail, and I just create a very large human centipede of vectors. Now, if you're asking, Professor, what is the human centipede? It is a horrible horror movie. It will give you nightmares, I guarantee it. But it's a rite of passage for modern day people. So I recommend that you watch it, but just make sure you haven't eaten recently because you might upchuck, you might vomit, put it that way. I almost did, I gagged a couple of times. But still, this is my human centipede, my tip to tail method. And the cool thing is that once you're done adding the vectors, tip to tail, tip to tail, tip to tail, then you go from the origin to the tip of the last vector that you added together in this human centipede connection. So here's the end of my second vector, the only one that I have that's added to A. So from the origin to the tip, this is my resultant vector. And what I want you to notice is that they're both the same exact thing. They give me the same results. I just get there a little bit differently. Now, one disclaimer that I really need to mention. The parallelogram method, because you're making a parallelogram that has 4 sides, the parallelogram method only works when you're adding together 2 vectors, because you're basically copy and pasting the other vectors to create the parallelogram, so you get 4 sides. If you're trying to add together 3 vectors, when you copy and paste, that'll give you 6 sides, and that's not a parallelogram. That's not a quadrilateral. That's not a quadrilateral. It's some other shape, so it's the wrong method. So when you have more than two vectors, the parallelogram method, not a good idea. Bad choice. The tip-to-tail method, the human centipede method, it's the best thing you got. It's the only thing you got. So keep that in the back of your mind. With two vectors, use either method. With three vectors or four or five or 1,000, whatever it might be, tip-to-tail method is going to save you. Parallelogram method is going to be an insane nightmare to try to boil down to two vectors if you're starting with 6 that you're adding together. It's gross, put it that way. Okay, well, what about B plus A? Because algebraically, I said that A plus B and B plus A, they give you the same thing. They're interchangeable. So how does that work geometrically? Okay, well, here I'm using which method? That's right, tip-to-tail method. So I move vector A from its quadrant 1 location, and I physically moved it to the tip of tail B. This is the end of my tip-to-tail method. Going from the origin to the tip of the last vector that I've connected together human centipede style, I get back this resultant, this vector addition vector. And it is identical to the one that we had on the previous page. Quadrant 1, very small angle, just barely above the x-axis, but it's the same. So geometrically, A plus B and B plus A are the same in this case. There are always exceptions, and that's something that we'll talk about in lab, for lab number 4 when we get there. But for most vectors, A plus B and B plus A are going to get you the same exact result. So let's go ahead and kind of deal with the circumstances that maybe it doesn't work so nicely. I'll kind of hint at it. So what do I mean by that? Well, in the previous slide, I said that there was no vector subtraction, and not really, but interesting subtlety. What we can say is that negative addition is really subtraction in disguise. And you're going to go, wait, what the hell? Negative addition? Well, think of it this way. 3 minus 2. Okay, 3 is positive, 2 is positive. You get positive 1 as an end result. But what if I were to give it to you this way? 3 plus negative 2. That still gives you 1, doesn't it? But it's an addition involving a negative quantity. But it gives you the same result as subtraction. So there is no such thing as vector subtraction. What there really is vector addition, but it's really called negative addition. So really what we have is this. But to be lazy, we could write it down like this. But technically, this doesn't exist in mathematics. Negative addition is what exists. So how does that look? Well, geometrically, this is the same A vector as before, quadrant 1, roughly about 45 degrees. This is the B vector, but now this is negative B. So what does that mean? Well, the vector will reflect in the exact opposite direction. It will be pointing in the exact opposite direction. So this is a vector that points straight downwards, having like a negative y component. So what is the opposite of negative y? Well, it's positive y. So that's kind of corresponding to negative b in this case. And once I have negative b graphed in my coordinate system, now at an angle of 90 degrees, as opposed to the unnegative vector at 270 degrees, I can now add them together, tip-to-tail method, my personal favorite, or parallelogram method, if you so desire. And this is the result that we're going to get back from this negative addition. It is a resultant vector. It is an addition of two vectors. One of them just happens to be negative, but it's a vector that now exists in quadrant 1 at a very steep angle. If you look at the other picture that we have right here of just regular vector addition, the vector was very shallow. The angle between it and the x-axis is very small. The angle between this other vector and the x-axis is much larger. So vector addition and vector subtraction give us different results in most cases. Again, in lab number 4, you'll be brainstorming when is it possible for vector addition and vector subtraction, quote unquote, to give the same value. There's really only 1 or 2 special cases, and they're quite dumb, to be honest, but you need to know them, and we'll talk about them in lab 4. But for right now, most other vectors, 99% of them, vector addition, vector subtraction, completely different results. Side note, and again, there's lots of these side notes in chapter 3 because it's such an important topic. I don't want you to get the wrong impression now and then get kind of destroyed, messed up in future chapters. Vector subtraction, aka negative addition, is not invariant. A minus B is not the same as B minus A. Why are they not the same? Well, in this case, I'm going to put the onus, the responsibility, on you. Take my 2 vectors and go ahead and create the graph, the vector diagram, as it's technically called, of B minus A, and see if it gives you the same result as A minus B. Hint, hint, it won't. But I really want you to do this yourself, even if it's just on a scratch piece of paper, even toilet paper, what the hell, why not? Draw B minus A. See what it looks like and compare it to this picture. See for yourself how they're not the same, why they are different. Okay, well, that was basically all about vector addition, negative addition or just regular addition. Now we're going to go ahead and switch to actually a much more complicated type of vector arithmetic, vector multiplication. And it turns out that vector multiplication, like vector addition, it can be understood algebraically with just a lot of symbols, gross, but yes. It can also be understood geometrically with pictures and diagrams, much easier to see, much easier to visualize. But unfortunately, there are 2 distinct ways to analyze vector multiplication algebraically and 2 distinct ways to analyze vector multiplication geometrically. So there's really 4 ways to talk about vector addition, 2 of them algebraically, 2 of them geometrically. And the question that you might have naturally is, why 4? Why not just 2, like with addition? The answer is how we multiply the vectors together. The first way that we can multiply vectors together is something called the scalar product. And when you're reading chapter 3 of the textbook, it will say in this section of chapter 3, optional topic. It's not optional because we have to use this vector multiplication as early as chapter 6. So my thought is, just like eating your vegetables, get it over with now. That way you don't have to that way you don't have to kind of choke down the broccoli later on. So scalar product, sometimes in math called the dot product, and I'll talk about why a little bit later on. It is the multiplication of 2 vectors, and this is the important part though, which outputs a scalar value only. Let that sink in. 2 vectors come in and just a single number comes out. That's quite interesting when you think about it, because in vector addition, it doesn't work that way. 2 vectors come in and another vector comes out. But now here, 2 vectors come in, no vectors come out, just a scalar, just a number. This is the definition of the scalar product. And what I want you to notice is on the left, the symbol between the first vector called A and the second vector called B is a dot, hence the dot product name. Cute, but relevant. This symbol here, again, this is the magnitude, the length of the A vector. This is the magnitude, the length of the B vector. Cosine, yeah, fine, whatever. But this is the Greek letter phi. This is a theta, this is an alpha. So that means that phi is a completely different symbol with a completely different definition associated with it. Phi, it represents the angle of something called the inner product space, When you take Math 26, linear algebra, this is going to make total sense. Until then, it will not make sense. So just like a stranger in a van offering you candy, don't question the candy, just take it in your mouth and hope for the best. I can't give you a good definition of what phi represents mathematically because it requires linear algebra, Math 26, to truly understand it. What we're going to say is to simplify the definition. Phi, it represents the angle between the two vectors in question. But there is a restriction to what the value of phi can possibly be. The value of phi, minimum is 0 degrees, maximum is 180 degrees. And it can be any number between those two. But the value of phi cannot be larger than 180 degrees. The reason why, again, has to deal with Math 26. But if phi is larger than 180 degrees, then that is an outer product space, which actually isn't the dot product, it's something else. So if you're talking dot product, which is physics 4a, physics 4b, physics 4c, phi has to be less than 180, larger than 0. Any other number, and it's just wrong. You're breaking a definition, and you can't break math to do math. It just doesn't work that way. But to understand what the scalar product is telling us, left-hand side and right-hand side, let's go ahead and do the actual multiplication outright, formally, we can say. So in this case, I've decided to do a 3-dimensional vector because, hey, why not? We'll go ahead and kind of bulk up the process. And again, my 2 vectors, A and B, I'm just giving them generic Cartesian labels, AX for horizontal component, AY for vertical component, AZ for azimuthal Z component, and then ditto for the B vector, BX, BY, BZ. They could be positive numbers, negative numbers, they could all be 0. I really don't care at this point. They're just numbers, they're symbols. But what I'm going to do is just like you had to do back in the days of algebra, if you have stuff in parentheses and you want to multiply, what do? First, outside, inside, last. You've got a FOIL. Because I have 6 terms that I'm multiplying together, 3 per parentheses, the foiling is gross. But here it is. I've got the first term, the middle term, the last term right here, the middle term to the first, the middle term to the second, the middle term to the third, the last term to the first, the last term to the second, and the last term to the third. Super, super gross. I know, I totally get it, but we're doing this the hard way the first time. We're kind of being dumb about this. We're just using what we know about arithmetic to understand what the hell is going on. As we're going to find out, there's a much smarter way to do this, but we don't know that yet. So we're just going to blindly push forward and hope for the best. Kind of like before with vector addition, AX and BX, they're just numbers. They're not I hat, J hat. They're not unit vectors. And I can always factor out numbers as much as I want to. And in fact, that's what I'm going to do. I've factored out all the numbers, all the components of the vectors, and I've left the dot of the unit vectors behind. And what's going to be important here is that the next part of this process, our book says by definition, but there's actually a way we can understand it, and I'll go back to that a little bit later on. But by definition, when you dot together, when you scalar product together, the same unit vector, I hat and I hat, J hat and J hat, K hat and K hat, the result is just a value of 1. Now, why is that? Let me go back. This is the definition of the dot product. This is the magnitude of the first vector, the magnitude of the second vector, and the angle between them. Well, let's look at I hat. It is a unit vector. So going back to the previous slides, what is the length? What is the magnitude of a unit vector? It's 1. So when I say I hat dot I hat. It's magnitude of I hat, which is 1, magnitude of j hat, sorry, magnitude of I hat again, which is also 1, and what's the angle between two identical, aka parallel, vectors? Well, if you use a protractor to measure the angle between two identical vectors, it's 0 because they're parallel. Doesn't matter if they're separate. We're using a protractor. We're talking about the angle between them, not the difference physically, Cartesian-wise, between them. So it's cosine of 0. And what's cosine of 0? Positive 1. So for unit vectors, I hat, j hat, k hat, k hat, it's 1, 1 cosine of 0, which is 1, so it's just equal to 1 in disguise. What about the other case? I hat and j hat, for example. Magnitude of a unit vector is 1. Magnitude of j hat, another unit vector, is 1. But I hat and j hat point along perpendicular axes. I hat is horizontal, j hat is vertical. What's the angle between x and y? 90 degrees. What's the cosine of 90? It's 0. So 1 multiplied by 1 multiplied by cosine of 90, aka 0, just gives you back a value of 0. And that's true for any of the mismatched dot products. Because of their orthogonality, because of their perpendicularness, the dot product of these different unit vectors is 0. And this is wonderful because 9 terms have the mismatched unit vector, so they're going to die out of the calculation. And the 3 that don't just have a value of 1 from their dot products. It's beautiful this way. So recognizing perpendicular unit vectors giving a value of 1, parallel unit vectors giving a value of 1, perpendicular unit vectors giving a value of 0 from the dot product, the result of the dot product just becomes this expression right here. And it turns out that this expression, this is called component-wise multiplication. Why is it called component-wise multiplication? Well, because you have ax multiplied by bx. They're both horizontal components being multiplied together for the first term in this addition. Same thing for the middle term. They're both vertical components of the two vectors being multiplied together. And same thing for the third one. Multiply, multiply, multiply. And then add together each one. And this is just a number. The I hats and j hats and k hats are gone. This is just a number. They're all gone. Same thing with this one. The result is just a pure number. The result that we get back is a scalar quantity. So the dot product destroys vector component information. It destroys vectors, to be short. It can give you a negative number. It can give you a positive number. It can give you 0. And in future chapters, when A and B are very specific physics variables, then the positiveness, the negativeness, or the 0 behavior of the dot product has very important significance for the behavior of that object. We're not quite ready for that yet, but at least we can understand how the dot product works and what it can kind of barf out as a final result. Now, to understand the dot product geometrically, it's a little bit trickier. But what I've done is just for 2 easy vectors, both of them are quadrant 1 vectors. Here's A at 45 degrees, here's B at 90. Theta A, this is the angle to the first vector, 45 degrees, give or take. Theta B, these 2 lines right here, this is the angle to the second vector, 90 degrees. This phi right here, this is the angle between B and A. So 90 minus 45, this angle here is 45 degrees. Doesn't have to be 45, could be any angle between 0 and 180, but it's just the angle between the 2 vectors. And the key thing that I want you to notice is that it's the smallest angle between the 2 vectors. I'm not going all the way around to get an outer product space. I'm going between the 2 to get an inner product space. But you'll notice something else that I've done. I can imagine that this right here and this right here can be two sides of a triangle. Admittedly, A is longer than B, so if I wanted to make a right triangle, it would kind of end right about here. But if I kind of made a triangle where this phi represented an interior angle, then this part of that triangle right here, this kind of what we would call it in this case, this opposite side right here, this would kind of correspond to our A cosine phi angle. And when you're thinking about it that way, maybe it doesn't make a lot of sense. So maybe think about it this way. This is like the hypotenuse, it just ends prematurely. This is like an adjacent side, it just ends prematurely. Go ahead and connect A to B, and now phi is an interior angle right here. Cosine represents this part right here as a result. So this interior angle, A cosine phi, just kind of represents this part of A projected onto B. How does that actually work? Okay, well, let's take this one step at a time. Here's the definition. A, just a number. B, just a number. Cosine phi, still just a number, still just a scalar. And scalars, the order of multiplication, doesn't matter. It's invariant. It's commutative, as you called it back in the early days. So I can change the order of multiplication, and I can associate two of the terms together with the associative property. A cosine phi multiplied by B. Why do I do that? Well, A cosine phi is really the part of A that is parallel to B. That's what this symbol represents, parallel to. This part of A is parallel to B, or technically in Math 24 and Math 26, A dot B, the dot product of A and B, is the projection of A as a vector onto B. It seems kind of weird, but the way that it works is that the second vector in the dot product, think of it as the ground. And think about, for example, the ground right now. Where is the sun relative to the ground right now? Well, if it's dark, don't answer. But if it's daylight, where is the sun right now? It's above the ground, shining straight down onto the ground. So imagine that my cursor is the sun shining down to the ground, B. Well, A is casting a shadow because it's in the way of my sunlight going to the ground, which is the second vector, B in this case. So A casts a shadow onto B. That shadow is given by A cosine of phi, where again, phi is the angle between these two guys right here. If phi is a very, very small angle, then it's going to cast a very long shadow. If A is a very large angle, then my sunlight is going to cast a very small shadow. Okay. Interesting side note. If I looked at it the other way around, so for example, here I did A cosine of phi multiplied by B, but if I looked at it the other way around, it still works out the same exact way. I associate the last two, and I have the projection of B onto A. So B cosine of phi would correspond to how much of B is casting a shadow onto A, where A is kind of the ground, and the sunlight is coming down in this direction here towards A, towards the ground in effect. So this idea of projection, if you take Math 24 and Math 26, they're going to talk about that a lot, especially in Math 26. But for Physics 4a, you don't need to know that projection, what it is, but it is kind of nice to know going forward because it's unavoidable. You're going to have to know what that is to get through that math class, to get through those math classes, I should say. Okay, well, this is the first way of multiplying vectors together, this idea of the dot product, the scalar product. Now we're going to focus on the other way of multiplying vectors together, the harder way of multiplying vectors together, something that's called the vector product, or loosely speaking, it's called the cross product. It states that two vectors are multiplied together, and the result is another vector that is unique to the first two. There is exceptions, of course, but it outputs another vector in effect. Here is the definition for the magnitude, the length of the vector product between two vectors. And what I want you to notice is that, again, I'm using the double symbol between A and B. Our textbook uses the single symbol, but unless you're like 70 years old, nobody uses that symbol anymore. Old people do, not younger people. But still, the magnitude of the cross product, the length of that vector, is equal to the magnitude of A, the magnitude of B, and sine phi. The phi symbol that you see here, it's the same phi symbol that we saw for the dot product. It is an inner product space, aka it's the angle between two vectors. And because it's an inner space, it's an angle that's less than 180 degrees. It's not an outer product space, which is an angle larger than 180 degrees. All right, so kind of a weird definition to start off with, the magnitude of the vector, not the vector itself. The reason why is actually quite profound, and we'll get to that towards the end of this discussion about the vector product. But let's just go ahead and kind of treat this like this way. So let me just go ahead and see if I can understand the cross product and what it's trying to tell me about vectors being added together. So here's what we mean by that. Again, three-dimensional vectors, and it turns out that the dot product, it works in R2, it works in R3, R4, R5, whatever you want. It also works for R1, but that's just really scalar multiplication. It's really not that different. It turns out that the vector product, the cross product, only works for R3, 3 dimensions or higher. It does not work for R2. It gives you nonsense if you try to use that method for R2. Why? You got to take upper division math classes. It's actually quite cool, but the cross product only works for 3 dimensions or higher. But nonetheless, why do we call it the cross product? Because we put a little cross between the two symbols for our two vectors. Now, when you were first learning arithmetic, multiplication, those two symbols, dot and cross, were used interchangeably. But now that you're in Physics 4A, now that you're in college and university, the dot and the cross are special symbols. So if you use a cross between two symbols, you're telling me that you're taking two vectors and crossing them together, not just multiplying two numbers together. You're telling me you have a cross product. If you put a dot between two letters, you're telling me that you're doing a dot product. If you don't want to do a dot product, if you don't want to do a cross product, put both values, put both symbols in their own respective parentheses. That tells me that you're multiplying scalars together, and therefore they're not vectors, and therefore we can move on. But if I see a dot or a cross in your work, I'm going to go scalar product? That doesn't make sense. Vector product? I think that's the wrong problem. That doesn't make sense here. What are you trying to do? So unfortunately, you were trained to use dot and cross for any multiplication, but that is 100% wrong. It just does not work that way. That would be like using the division symbol when you were trying to add numbers together. Yeah, they look the same, but they are not the same. They are completely different definitions. So here are my three vectors, and I could FOIL this out. It would be gross again, even more so for the case of the vector product. So what I'm going to do is I'm going to introduce a different way to evaluate cross products of vectors. That way that I'm using is not going to be FOIL. It is going to be using something called a determinant. If you've taken Math 4A, 24 or 26, especially Math 26, you know determinants. You know Wronskians. Great, awesome. If you haven't taken those classes, this is going to seem weird, but basically the determinant is a method of evaluating the cross products of vectors, a vector space, if you want to be technical about its definition and its categorization. And it's given by this symbol on the right-hand side of the equal sign. It's just a very, very long single line, not absolute value symbol. That's a short line. This is a much longer line. And it contains 9 symbols, 3 by 3, 3 rows, 3 columns. The first row in the determinant they are going to become eventually the unit vectors of the output vector, the unit vectors of the multiplication of A and B in this manner. The next row, these are the components, horizontal, vertical, and z, of the first vector in the multiplication. The third row are the three components of the second vector, b in this case, horizontal first, vertical in the middle, and then z at the end. The order has to be this way. If you change the order of these 9 symbols, you're going to get garbage at the very end. You're just going to get nonsensical results, and we don't want that for this early in the semester. So because the output of the cross product is a vector, then that means that we're going to have to figure out what is the I hat component of the output vector, what is the j hat component of the output vector, and the k hat component of the output vector. We're going to take it one piece at a time. We're going to isolate the I hat component of the output vector in the determinant. And then once we're done, we'll switch to the j hat and then the k hat afterwards. So if you've seen this method before, great. If you haven't, hold on to your butts. We're going for a ride. First things first, I've put parentheses and a subscript of x around the cross product to drive home the fact that we are looking for the x component, the I hat component, the horizontal piece of the cross product vector. So this isn't a cross. It looks that way, but my crosses and my x's look identical, sadly. I try to make. But if you want to isolate the I hat component, then what I do is I put a circle around it. You don't have to, but it just really emphasizes that this is what I'm focusing on. But what you have to do is you have to draw a vertical line straight down from the I hat symbol and a horizontal line straight through the I hat symbol. You're crossing out 4 pieces of information such that only 4 pieces are left that are going to go into the calculation of the component itself. How do we find the actual value? We subtract the multiplication of the remaining diagonal elements of the determinant. They are multiplied in this order, and this is sometimes called butterfly multiplication because it does kind of look like a butterfly. So here's one diagonal, so these are going to be multiplied together. Here's another diagonal. They're going to be multiplied together, and I'm going to subtract the multiplication of diagonal and diagonal. Okay, what order do I subtract them? Left is first, right is second. So diagonal right is first, diagonal down left is second. So it's going to look like this. This is the horizontal component of the cross product vectors. Here's something I want you to notice though. It's the x component of the vector, and look what's missing on the right side. A subscript y, not x. B subscript z, not x. Interesting deficiency of symbols. Turns out not by accident. We've found a pattern. If you want to figure out the vertical and the z component of the cross product, you're just going to literally do the same exact thing. So for the j hat component, what you've got here is I want the j hat component, the y component, the vertical component. So that's where the symbol of y comes into play. I circle j because that's what I want. I draw a horizontal line through j, and I draw a vertical line through j. These are the only 4 pieces left, and these are diagonals, so I need to multiply them and then subtract that multiplication. So the vertical component of the cross product is going to be ax multiplied by bz subtracted from az minus bx. Again, what's missing from the right-hand side? No y components of a or b, only x and z. Just like in the previous step here, the x component only had y and z, no x's at all. So I bet you that if you were to use enough willpower, you could make a hypothesis as to what the third component would look like. In terms of a diagram, again, I'm looking for the z component, that's fine. So therefore I draw the horizontal line through the k-hat, a vertical line through the k-hat, and here are my diagonals, my butterfly, that I'm going to be kind of forming through subtraction. So downwards right, downwards left, downwards right, downwards left. So here are my kind of y components. But, and this is really sad, but there's one small problem. We have one small issue to deal with. It turns out that for the cross product, something is inserted along the way. Can you see what it is? Hint, it's in the middle. Here's the x-hat component. Here's the y-hat component. Here's the j-hat, sorry, here's the k-hat component. Plus, plus, minus. Where did the negative sign come from? Well, it turns out that it comes from something in math called permutation theory. If you want to understand permutation theory, you've got to go to grad school. That is the only time that I remember learning about it. Up until that time, it was just basically, it's negative, shut up and deal with it. Maybe not so harsh, but it's basically, it's negative, don't ask questions. Stranger in a van with candy. Just take the candy, don't ask questions, you're going to be fine. So we have to throw in a negative sign for a very bizarre reason. But what that basically means is that this middle term that we found, all that happens is that the order of subtraction reverses. But otherwise, it's the exact same process. So this is kind of what we have going on here. The negative sign I've left there just to kind of match math textbooks. Yay, wonderful, good times. But the key thing about this output vector is that it has unique x, y, and z components, I hat, j hat, and k hat components. And if I wanted to, I could figure out the magnitude of this vector, the length of this diagonal of the period, sorry, of the pyramid, because we're in 3 dimensions. We can't say triangle for Pythagorean theorem because that's 2 dimensions, that's R2. But I can figure out the length of this vector by taking the square of this one, the square of this one, and the square of this one, however ugly they might be, and just add together the squares, take the square root, and boom, there we go. Pythagorean theorem on 3-dimensional steroids. Okay, again, more disclaimers, more side notes. Less relevant in chapter 3, insanely relevant in chapter 6 and beyond. A cross B is equal to negative B cross A. That doesn't make sense for numbers because 4 times 3 doesn't equal negative 3 times 4. That doesn't make any damn sense. Why is this true? Well, if you change the order of the vectors going into the cross product, here's what you've done. Because B is the first vector, then this middle row would be Bx, By, Bz. Because this is the second vector, it would be in the third row. This would become Ax, Ay, Az. The subtraction would be reversed because you have reversed the information going into the determinant. So if the subtraction is being reversed by you changing the order of the cross product, to make it go back to normal, you have to forcibly add in a negative sign to the parentheses on the right-hand side. Crazy but cool. The other thing is that, kind of like with the dot product, if I take the cross of identical unit vectors, the result that I get back is 0. It's only when we have different unit vectors that we cross product together that I get non-zero results, other unit vectors. And here's kind of how that works, roughly speaking. I'll deal with the top row for right now. I'll talk about the other rows a little bit later on. But going back to that previous slide, right here, if I have two identical vectors, I hat and I hat, for example, the magnitude of I hat is 1, the magnitude of I hat is 1, and because they're parallel vectors, the angle between them is 0. So 1 times the sine of 0. Well, what's the sine of 0? Right, it's 0. And any number multiplied by 0 is 0. Okay, so now what? Well, here's the issue. This definition here in the top, this is the magnitude of the cross product. And we are now saying that for I hat cross I hat, the magnitude of that cross product is 0. Okay, well, if the length of the hypotenuse of that pyramid is 0, then the x, y, and z components also have to be 0. Why is that true? Well, how do you calculate Pythagorean theorem? A squared plus b squared. Well, what if a and b are negative? Well, you're squaring them, so it doesn't matter. So how can two numbers, when they're squared and added together, equal 0? Well, you might raise your hand, Professor, they're imaginary. Okay. In physics 4a, we only deal with real numbers. We're in the real plane. We're not in the imaginary plane. So we can't use imaginary numbers. They don't exist in reality as we understand it in physics 4a. So if the two sides of my triangle can't be imaginary, they can be positive, negative, or 0, and I'm squaring them and adding them together, and the result has to be 0, the only way that that works is if x, y, and z are all identically 0, aka it's the 0 vector in disguise. It's 0 in effect. The other cross products, they are trickier to explain. I will have to use the geometric method to explain why these 4 identities are true. And I think I forgot 2 of them. I did forget 2 of them, I and k, and then k and I. My apologies, I forgot to add them in. But these 4 identities here, they can be justified a little bit later on. But the one thing I want you to notice is that, again, changing the order of the cross product adds in a negative sign along the way, just like it kind of did right here. Okay, to understand that last part of the side note with different unit vectors, let's look at this picture, this diagram, this graph, if you will, of a cross product. And I'm just choosing easy vectors because I want to make my life easy as possible. I've chosen the vector A to be completely horizontal, only along the positive x-axis. I've chosen the vector B to be only vertical, only along the positive y-axis. And it turns out, interestingly enough, the cross product is only along the z-axis. So how do I know that this is true? Why is this picture correct? Well, if I wanted to give you the components of the A vector, the vector only exists on the x-axis, so the y and the z component are 0. But it's going to have a length of a. So that means that the x component has to be positive a. Same thing with the b vector. It's only vertical. It has no x or z component, so it's 0 and 0. But the magnitude of b is b, and it points up, so therefore it has a positive y component of b, in effect. So if I go through the arithmetic, if I go through the algebraic method, one step at a time. So here's my y component and my z component, my z and my y, and then ditto and 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 ditto. The result that I'm going to get back is a vector that doesn't point along the x, doesn't point along the y. It does point along the z-axis in a positive manner by this amount. I don't know that amount, so I just kind of chose a random length, a random magnitude, but it only points along the z-axis. Here's something I want you to kind of notice. Look at A, B, and their cross product. What do you notice about them? Well, A and B are perpendicular. Yes, that was my choice. They didn't have to be. I just chose an easy one. But what do you notice about the cross product compared to just the A vector, the cross product compared to just the B vector? What do you see? Well, what I see is I see that the cross product is perpendicular to just the B vector. The cross product is perpendicular to just the A vector. And that is something that is true for every cross product. And I'm going to use the math definition. The cross product vector output is perpendicular to the plane of the space spanned by the two vectors going into the calculation. And that's not going to make a lot of sense. That's a huge mouthful. But I'm going to simplify that when we talk about the geometric interpretation of the cross product. That long definition that I gave before will make a lot more sense afterwards. Here's something kind of interesting too, though. If I want to find the magnitude of this vector, one side of my pyramid, another side of my pyramid, another side of my pyramid, squared, 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 take the square root, I get AB. Okay. Well, if I multiply any number by 1, it doesn't change anything. But if I say that 1 can come from a trigonometric argument, say, for example, sine of 90 degrees, then what's going to be important about that is if you look at my two vectors, A and B were chosen to be perpendicular. Holy crap, it worked out. Doesn't always work out this beautifully. I kind of chose a very special case, a very kind of sweet case for us to start with. But the key thing is that I can kind of work backwards to get the definition, which matches the vector that it descended from this very nasty calculation up on the top. Okay, but really to figure out where the cross product vector was pointing, I didn't use this long bloated technique. I used a different technique instead as a shortcut. And this is a technique that you're going to have to learn. There's just no easy way around it. If you don't learn this technique, you're going to struggle in this class, guaranteed, and you're going to outright fail Physics 4B, guaranteed. What is this technique that I'm referring to? It is something called the right-hand rule. As you see here by the definition, the right-hand rule is a method using your right hand to determine the direction of the output vector of the cross product of two vectors. Okay, what does that mean? How does it work? What the hell is going on? All right, well, let's just take it one step at a time. Let's learn the rules of the right-hand rule. Let's learn the procedure of it. So first things first, point the 4 fingers of your right hand parallel to the first vector, A in our case. The second step in this procedure is curl those same 4 fingers into the flesh of your right palm. And this is going to seem weird, but think about it this way. Let's say that you're outside and from a distance you see a friend of yours and you want them to come closer to you. You hold out your right hand, and what do you do with your fingers in your palm? You kind of curl your fingers into your palm, gesturing them, hey, come towards me, come here, come here. That motion that you're doing with your fingers into your palm, that's what you're doing here as well. But as you're curling your 4 fingers into your palm, kind of like in a come here kind of motion, there's 2 things you got to be careful of. The first thing is that as you're curling your fingers into your palm, at some moment in time during that curling motion, your fingers should point parallel to the second vector, B in our case. If you're doing the come here motion with your fingers and your fingers never point in the same direction as B ever, then turn your wrist over 180 degrees and do the come here motion, but now with your fingers facing downwards. I know it's kind of weird. Or turn your hand the other way to where your fingers are facing the opposite direction. And then curl your fingers and see if the curling of your fingers will now point along B, the other vector, at some time during the motion. If you have to bend your wrist in a painful way, you're doing it wrong. You're doing the outer product, not the inner product. Turn your wrist over and then bend your fingers and see if you can get to the other vector in a more natural inner product sense. The other cool thing about this method of the right-hand rule, there's more than one, but the reason that I like this version of the right-hand rule is that how far you have to rotate your fingers in the come here motion, that is the angle between the vectors. So you kind of get an idea for how big the angle is between the vectors by using this version of the right-hand rule. Is it acute? Is it obtuse? Is it 10 degrees, just a little bit of a come here motion? Is it 95 degrees, a huge come here kind of motion? That's why I like this method better than the other one. But the other one does work, and if you want to learn about it, that's fine, but you can learn it somewhere else, because this one I think is infinitely better. This is the one that's used in math all the time. The 3-finger method of the right-hand rule, they never use it in math. They're going to look at you and go, what the hell are you doing? This doesn't make any sense. But if you use this method, the curl of your fingers, the rotation of your fingers, and the come here motion of your right hand gives you the angle between the vectors, your inner product space, in effect. And once your fingers get to that second vector, stop. Don't do the complete come here motion. Stop when you get to the B vector. And then stick out your thumb, extend your thumb, kind of like you're doing a weird thumbs up, but maybe it's kind of tilted left, right, towards your face, I don't know, whatever it is. But extend your thumb outwards. Your thumb is parallel to the output vector of the cross product. So for example, how would it look in this case? A is pointing downwards, B is pointing in the Z direction. Without knowing A, X, A, Y, A, Z, B, X, B, Y, and B, Z, how could we find the general direction of the cross product using the right-hand rule? All right, well, I'll give you a hint. Don't forget that each axis is perpendicular to another. So is there an axis which is perpendicular to both A and B simultaneously? In our case, yes, the negative x-axis. Point your fingers downwards towards A of your right hand. Curl your fingers towards your flesh. As I'm doing it, I can easily see that my fingers are pointing along the Z direction, and when I stick out my thumb, it points to the left in the negative X direction. If you try to do it the other way, you're going to have to break your wrist to get your fingers to go from A all the way to, okay, I can't do it, to B. So that's an outer product space. It's no good. So I have to curl my fingers from A to B, and my thumb points to the left consequently. So that would be the direction of my cross product vector. One little disclaimer. I'm deliberately choosing easy vectors. A is only along the y-axis, B is only along the z-axis. If you just have a vector A that points in x, y, and z simultaneously, if the B vector points in x, y, and z, then the cross product won't only point along the z. It won't only point along the y. It won't only point along the negative x. It'll point along a combination of x, y, and z simultaneously. You'll have to actually figure out the cross product using that nasty kind of method from before to get the non-zero I hat, non-zero j hat, and non-zero k hat for the uglier version of the cross product. But for these nice easy cases, it's z or negative x or whatever it might be in that case. So this chapter is a fairly short one, but it's very, very deep. It's very, very dense. So what we're going to do is we're going to end today's class with just a longer than normal example problem that will kind of encapsulate all the different ideas and all the different methods and techniques that we have learned along the way. So here is our example problem. And you'll notice that I've chosen very conspicuous symbols for the two vectors. Delta R1, delta R2. That choice was not by accident. This is a nice stepping stone into ideas like displacement in chapter 4. Okay, let me not ruin the surprise too much there. So the first part of this question is asking for the two vectors that I'm giving you, are either vector a unit vector? And then explain. So, all right, might need to pause for a second, but what is a unit vector? What is the definition? What is the behavior of a unit vector. It's a vector that has a length of 1. So let's go ahead and figure out the magnitude or the length of delta R1 and delta R2 and see if they're equal to 1 or not. If I look at the first vector, the magnitude of that vector, again, we're in 3 dimensions, so I kind of use the pyramid version of Pythagorean theorem. 3 squared plus 0 squared plus 1 squared. I get a value of 10. Okay. What about for the second vector? What do you think is going to be the output of this process of finding the magnitude of delta R2? It's the same thing. It's 1 plus 0 plus 9, taking the square root is root 10. Are either of those numbers equal to 1? No. So neither vector is a unit vector, and that's because the magnitude of both is equal to square root of 10, which does not equal 1. That's my explanation. No is my answer. Okay, pretty straightforward, but again, unit vectors don't have to have the little caret or the hat symbol above them. They should, but they don't have to. And my apologies, I forgot to add the little arrow symbol inside here and inside here. That's an omission, my bad on that part. Let's go ahead and take a look at the second question. And admittedly, for the homework problems, you might have to graph once or twice, but a lot of the problems that are at the back of the chapter problems, they do ask you to graph things. So just be prepared for that. If this were on a test, and again, I make no promises, but if you had to do vector addition graphically on a test, I'm not going to bust out my protractor and make sure that you're accurate. I'm not going to bust out my ruler to make sure that you're accurate. But if this were on a test, if the addition of vectors is supposed to be in quadrant 2 and your answer is in quadrant 3, it's wrong. End of story. But as long as yours is close, it's probably going to be good enough. If the arrow is supposed to be long and your arrow is almost a 0 size, okay, you've made a mistake there. But in general, for a test, I'm not too picky about the accuracy of drawing vector diagrams, addition, things of that nature. But you do kind of have to be in the ballpark. So you just keep that in the back of your mind. But again, the goal here is to graph these 2 vectors added together. Okay, so let me just go ahead and take this one step at a time. So here's the first vector written in standard, aka Cartesian form, just numbers 3, 0, and 1. And then I'm adding that to the second vector, also written in standard form, just 1, 0, and 3. And like before, I'm just going to go ahead and add together the identical components, 3 plus 1, 0 plus 0, and 1 plus 3. And I get back 4 for the I hat, 0 for the J hat, and 4 for the K hat. Nice, easy vector. Because it's 3-dimensional, I have to be careful how I graph it. So here's what I've got. X, horizontal, Y is vertical, Z is kind of forwards, backwards. The picture looks like it's going downwards, but that's just an optical illusion. This is a diagram. Here is the resultant vector. 1, 2, 3, 4. So here's the X, 0 along the Y, 1, 2, 3, 4 along the Z. So it points from 0 to 4, 0, 4 at this point. I've also drawn this in terms of the parallelogram method. I didn't have to do that, but I just wanted to show you what it would look like in this case. So here's delta R1. So 3, 0, and 1. So there's the first vector. The second vector is 1, 1, 2, 3, and 0. So here are the 2 sides of my parallelogram. I copy and paste one side. I copy and paste the other side. From the origin to the vertex, there's my delta R1 plus delta R2, nice and easily drawn in this case. Not artistic, not very well drawn, but close enough to where you can recognize that, yeah, I see what's going on. It's not in the y-axis at all. It's flat in that regard. Part C. Determine the value of the scalar product delta R1 dotted with 3 delta R2. Now this is weird because there is a scalar mixed with a vector on the right-hand side of this expression. Well, don't forget that the word scalar comes from the prefix scale. which just means changes the value of, makes it bigger or smaller in effect. So let's just go ahead and take this one step at a time. Here's delta R1 in all of its glory. Here's delta R2 in all of its glory. And here's my scalar out in front. What can be factored out can also be pushed in through the brackets or parentheses. So I've distributed the 3 to the first component, to the second, and to the third, getting 3, 0, and 9. Once I have the two vectors written in their standard form with the scalar value of 3 absorbed into the vector, I can now go ahead and do component-wise multiplication. I hat multiplied by I hat, j hat multiplied by j hat, k hat multiplied by k hat, and then add the results together to get a value of 18 in this case. And now for this kind of ending part of the problem right here, we're going to be asked to calculate the cross product of delta R1 crossed with delta R2. Now, admittedly, because it doesn't have the little vertical bars around them, I don't want the magnitude of the vector. I want the actual vector itself. I hat, j hat, and k hat components specifically solved for. So here I'm going to go ahead and set up my determinant. Output vector components, first vector, second vector. Again, order does matter. Delta R1 goes first, delta R2 goes second. Using that whole process, 0 times 3 just gives you 0. 0 multiplied by 1 gives you 0. The minus sign comes from the permutation theory that we don't care about. For the j hat component, 3 gives us 9. 1 times 1 gives us 1, and we're subtracting. For the k component, 3 times 0 gives us 0. 0 times 1 gives us 1. And therefore, simplifying this result, the end value that we get back is 0, -8, and 0 for the cross product. And again, this kind of makes sense because this vector doesn't point vertical. This vector doesn't point vertical. So what is a vector that is perpendicular to both? Well, probably a vertical vector. Makes kind of sense in this case. Oh, that's right. I did add in one more question at the very end. I forgot about that. So for this last part of the problem, we want to figure out, okay, what is the inner product space? What is the angle between the two vectors, delta R1 and delta R2? So this is where I'll use the other definition, this really kind of starting definition of the cross product. And what you're going to notice here is that, again, from part A of the problem, I already know the magnitude of the two vectors, so I can just go ahead and recycle that information. Just as a reminder, information can feed forward, never backwards. So if you're solving a problem and you say, see problem F, and it's only part A of the problem, I'm just going to cross it out and go, nope, that's future information. You can't use today's lottery to win yesterday's lottery. It doesn't work that way. So I can use A to solve E. I cannot use E to solve A. It does not work in this class that way. You cannot go backwards in time, back to the future style to fix the problem. But nonetheless, moving forward, I have the vector of the cross product. This is the magnitude of that vector. So I can just go ahead and say, for my pyramid version of the Pythagorean theorem, this component squared, this component squared, this component squared. Magnitude, magnitude, I have root 10 and root 10. Sine of the angle between the two vectors, don't know that information. That's my unknown quantity. I've got 8 right here. I know I've got 10 on the right-hand side. So if I want to solve for phi, I divide by 10 and take the arc sine of that fraction. And the result that I get is 50 degrees in this case. Now, a question that's been asked to me in the past is, well, Professor, could we have solved part E using the definition of the dot product? And the answer is sure, yes, of course. However, the answer for part C has a value of 3 inside the dot product. Your version would not. Watch out for that. So technically it's a different vector, so therefore the angle between them could be different. Now, admittedly, you're going to look at this and go, well, wait a minute, professor, when I take the arc sine of 8 over 10, I get 53 degrees with a bunch of decimal places afterwards. Well, don't forget, all of my numbers leading up to this point, 1 sig fig, 1 sig fig, 1, 1, 1. This is 1 sig fig. This is really 1 sig fig in disguise. So I have to round down to one significant figure to get the correct answer. And again, this is something that you have to do on the homework and you have to do on the exams to get full credit. But beyond that, this very long example problem should hopefully now give you an idea of how to understand unit vectors that lead to vectors, aka unit vectors describe vectors. This idea of adding vectors together, subtracting them, which is really just negative addition, multiplying vectors together, dot or cross product, depending upon what it says, and just keeping in mind that if you have values like 3 in front of a vector, they scale the vector. They make it larger or smaller, depending upon what the value is in the first case. So that's it for this lecture. It's very, very long. It's very, very deep. If you have questions about this problem or just about vectors in general, please ask me now. Chapter 3 is instrumental to chapters 4 to 15, literally the rest of the semester. So I want to make sure that you guys have a strong foundation going forwards. Otherwise, you will fail. If you don't understand chapter 3, you will fail. And I don't want you to be in that situation because it's just not good for you or for me or anybody in that effect. But otherwise, that's it. Thank you guys for listening. And I will go ahead and see you guys for our next lecture activity next week.